So because I'm looking for the vertical center of mass, I did a horizontal slice, and I'm going to add up all of my horizontal slices from 0 to 1. And that horizontal slice has a thickness dy, and it starts at position x and it goes out to position 1. I went ahead and used the function to find the area of that graph, and so that's just evaluated from 0 to 1 of the integral that's x squared dx, and found 1/3. And then I'm going to use the normal center of mass equation, which is 1 over m integral y dm, but I need to know what dm is. So I'm going to use dm over dA equals m over a, so saying that the density is a constant throughout. So the area of that little slice is going to equal, well, the piece from x to 1 is equal to 1 minus x, and then times the vertical height, which is dy, and then that equals m over a, where I know that the area from above is 1/3. Then I'm just going to use some algebra to figure out that dm equals 3m times 1 minus x dy, and plug that in over in the center of mass equation. So, but the problem here is that I have x in that, and I need x in terms of y. So I'm going to have to find that equation. Well, I'm going to use what we started with, which was y equals x squared. Sorry. And so if that's the case, then x equals the square root of y. And I can plug that in instead of x. Notice that the m's canceled, and then the 3 comes out front, and so I have y times 1 minus root y. What I did was I squared the y to put it inside of the radical, so when I distributed through 1 minus root y, it became y minus y to the 3 halves. And so then when I integrated that from 0 to 1, because I need to add up the slices, from the origin up to the highest point that's shown in the graph, which is at 1, it became 1/2 y squared minus, and then 3 halves, you add 2 halves, it becomes 5 halves, flip it, so 2/5, and then evaluate that from 0 to 1. And so we end up, I just did some algebra here when I plugged the 1 in, and you end up with 3/10 for your answer.